Okay, we are pretty much at time, I think. Yep, okay. Let's do this thing. All right, welcome, welcome. Welcome back to 150 lecture. I see there's still quite a few of you, so I didn't lose too many of you, it seems. But here we'll be talking about equivalence, binding, and scope. I hope you had a good lab on Wednesday. Your TAs are working really hard for that one. I know that there's a lot of stuff covered in lab that we didn't get to on the lecture on Tuesday, but today we'll be talking about it in more detail, hopefully, okay? Now, I know that my first slide on Tuesday was drab and dreary and black and white. That's because the colors of 150 are black and white. But functional programming is not drab and dreary. It's colorful and cool. Hence, we have these slides right here. So let's get into it. Let's get hype, okay? Before I get into the actual lecture, though, there's some administrivia I have to tell you about, which is namely the house system. You might not be able to see, but you all picked names on Wednesday. And I did say that the house with the best name would get the first 15 points. And I have to say that there is, I've chosen the winner. Okay, so to recap, we have the red house, which is house blue team. We have the yellow house, which is house yellow, headed by Nancy and Steven. And then we have the blue house, which is house I love Brandon. Well, see, I'm an instructor. I don't take bribes. So the winner today is going to be house blue team. It's also unclear whether or not I love Brandon was me or the TA. So, you only got half of the flattery anyways. So I'm going to fill this in. That's 15. Whoops. What? That's 15 points. But that's okay, because the first 15 points isn't going to mean a whole bunch. We're going to have a quiz in the middle of lecture. Remember, you're not counted for a grade, but the winning house will get another, 15 points, sure, let's say. So be wary of that, all right? That will be coming, okay? Congrats, house blue team. You genuinely made me laugh. Okay, cool. Let's get into it. So, equivalence, binding, and scope. I told you a bunch of high-level ideas about how state is bad, how functional programming is different. But today, I'm going to concretize some of those ideas, because I didn't show you the goods. I didn't show you how that was true. So our lesson plan for today, we're going to be talking about types again. We're going to be talking about more types of functions than the one I showed you in lecture Tuesday. We're going to be talking about binding and scope. Whoa, what is that? Oh, it's my cursor. We're going to be talking about binding and scope, which is the main difference in terms of mutability, or how this idea of changing the world, I said on Tuesday. We'll talk about pattern matching, which is a nice way of how we can sort of manipulate values in SML. And then we'll talk about equivalence, which brings in math into this whole thing and ties a nice ribbon on it. Okay, that's clear. Yeah, this is good. Okay, cool. All right, let's get started. So last time, just to recap, we learned about expressions, values, and types. We learned the mantra, well-typed expressions. Only well-typed expressions are evaluated. Remember, ill-typed programs do not run, all right? Memorize that. Say it to yourself at night when you sleep. And then expressions can do one of three things. They evaluate to a value, they raise an exception, or they loop forever. Nothing else, nothing more. And we also saw some typing rules, which are how SML knows that the expression of the type of an expression. Jesus. Okay. And this is purely a recap, so don't feel the need to write this down. If I'm going too fast and you want time to write stuff down, just be like, hey, wait a second, and I will happily wait. But remember, these slides will be posted after. Okay. More types. I showed you some types on Tuesday, but I didn't show you all of them. So there's a few basic ones. But I'm going to tell you that right now. I'm going to use the board for this lecture. They are int, and some values of this include 1, 150, and 132, let's say. We also have the type real, which is the type of real numbers, like floating point numbers. So we have 0.0, 0.1, 2.0. We also have bool, which has precisely two values, which are true and false, right? This should not be unfamiliar. We have the type of strings, which has such strings as the empty string, hello, and I don't know, x. And then finally, we have the type of characters, char, or car, however you want to say it, which is car. And then the way you phrase it is kind of weird. You have to put this hashtag quote a hashtag quote B. This is not super critical to know about, but these are like some of the basic types we're working with in SML, okay? And they're all listed there. But these are just what we call base types, right? They're like the default types. They're like the standard ones that are available. So we're going to see that they get actually a lot more interesting, okay? Cool. We also have this notion of tuples. So tuples. A tuple is a collection of values. If I want to store something, maybe I don't just want an int. Maybe I don't just want a string. Maybe I want a string and an int. Okay? So a valid tuple might be something like 1, 2. Okay? This is a tuple where the first component, I'll say, is 1. The second component is 2. And a tuple has its own kind of type. We say that this type is going to be called a tuple type. So it'll be, the first thing is an int, right? So it'll be int star int. Int cross int, int star int. That's how we usually will say it. You probably saw this in lab. But we have our own notion of tuple types, or product types, they might be said, by some really fancy people. And this itself is a tuple. Okay? So we have some more examples up there. A tuple can have any number of things in it except for 0 or 1. Okay? You have 2 things in a tuple, you can have 3 things in a tuple, so on and so forth, but you can't have 0 or 1. And we call that a product type, right? And when I'm talking about like code of a tuple, it evaluates from left to right. So if I had something like 1 plus 1, 2 times 3, using the notation we learned last lecture, I would first step the leftmost component that is not yet a value, right? So I would say this steps to 2, because I evaluate this guy. And then I would keep 2 times 3 the same, because I haven't taken a step on it. And then that in turn, and I'll, well, OK. Def of add. So I actually made this remark in a later slide, but when we're doing like a trace like this, when we're stepping code, usually on the right-hand side here, we're going to want to cite how that step happened. How do we know that this thing stepped to that thing? Well, I know that this happened because 1 plus 1, by the definition of the add function, of the plus function, needs to step to 2. So I do a little citation here. And there's a nice way to format this in LaTeX, but I'm not going to go over that right now. And then once I have this thing, it's not yet a value. So because there's this thing, right, that can still be evaluated. So what I'm going to do is I'm going to step it again. 2 will stay the same, and then I'm going to get 6, right? Is this now simplifiable? Can I still simplify this? What do you think? No. I'm hearing no. Yep. This is now a value, right? So you know, this thing, hook right arrows to 2, 6, right? It evaluates to a value, and that value is 2, 6. So that's how we evaluate a tuple, all right? It has its own typing rules. It has its own evaluation rules. Any questions on this? Yes?
So let's say the first entry had to, like, let's say, take 3 steps to evaluate. It would do all those 3 steps before going on to the right.
Yep, yep. Every single entry from left to right has to be a value before we can go to the next one. Yep, good question. Yeah. Wait, sorry, what? Are we voting? Oh, are reals floats? I'm not going to get into that right now. Ask on Piazza. It's a good question, but let's not get into it. There's a good answer to that. Cool. And then the typing rule is that if I have, you know, e1, comma, en, then if I know that each of these components has a certain type, call it t1. So e1 is of type t1, and then all the way down to en is of type tn. Then this whole thing just has type e1, or sorry, t1 star tn. I know I'm making liberal use of these ellipses here. Does everyone understand what I mean? I just mean, like, you know, if you keep enumerating this, you can do this any number of times, except for 0 and 1. Okay? This is the typing rule for tuples. And then parentheses matter. If I have, you know, 1, 2, 3, this is a different value than the tuple 1, 2, 3. Why? Because this thing has 2 things in it. The second thing just happens to be a tuple. This thing has 3 things in it. Each thing is an int. The types are also different. So this one would have type, I'm running out of space here, but this is going to be a type int star parentheses int star int. Okay? But this thing, right, is going to be of type int star int star int. So the parentheses here do matter. Usually in math, we can just discard parentheses. Doesn't matter, right? But here it does. All right? Is this clear to everyone? Okay. Yeah. When communicating as humans, yes, but the actual type, would actually be int star, da 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 da, right? We're talking about the actual objects as like communicating. Like if you say that to me, I'll know what you mean. But practically, like it is actually right the iterated like star of int 50 times. Yeah. Although it should never come up in practice. You have a tuple of 50 things. Okay. All right, so we sped through that, but those are some things about tuples. All right, next we're going to talk about some things about functions, and then I think I'm going to erase this while I talk. Okay. Okay. So functions. We talked about functions. I showed you one function, but there's a lot more of those. In particular, so we saw how star could be used to make types out of other types, right? If I have int and int, they are both types. I can put a star between them, and I'll get the type int star int. So int star int, this thing kind of makes types out of other types, right? In a similar way, we're going to talk about this function type thing. We put an arrow in the type. So I told you about this double function, which takes in an int and doubles it, right? So we said that double is of type int to int, I'll say. Okay, int arrow int to int. These are valid ways of saying the same thing. This thing also makes types, right? So we call it a type constructor. Okay, and arrow is one of them. So we can have a more advanced notion of types when we have like nested product types, nested tuple types, like int star int, or star bool. Let's switch it up. But we can also have like a nested concept of a type where we have int arrow int. And we'll see later on in this semester that this idea stretches even farther than what I'm telling you now. Okay, that's a function type. And then we have, for instance, double of type int arrow int. We also have like not, which is the SML function for logical negation on booleans, which is of type bool arrow bool. Okay, clear enough? Okay. So we also have this idea of lambda expressions. When I showed you the double function, we did it via a declaration. We said fun double n colon int equals n plus n. This is a fun declaration. But lambda expressions, these things called lambda expressions, let me show you what it is first. Okay, this is what we call a lambda expression. So we use this fn keyword. Yes?
Question about
So the spiritual answer I'll give you here is, what are floating points? I don't know what floating points are. In this class, we do not know what floating points are. We do not care about the intricacies of floating point arithmetic. Floats are reals, reals are reals, reals just add. Also, the integers are unbounded. That's another thing that we assume in this class. There are no maximum integers in this class. But yeah, that's another good question. Yeah, good question. Cool. So lambda expressions look like fn, and then they take in an argument. So I could say n colon int. And then I say this arrow, which is 2 characters, equals and then greater than. And then I write n plus n. This is what's known, this is an expression. All right, I can bind this to a variable and everything. It's an expression the same way that 2 and 3 are. It's also a value. What this is it's a function that takes in a number and doubles it. It is the double function. But I can't like put this on my line and then use it. Okay, I need to first bind it to something. This is an expression. But what I can do is I can surround it in parens and then put it next to 2. Okay, so now this is the application of this lambda expression to 2. And I'll see that this evaluates to, it steps to, sorry if you can't see this, 4. It steps to 4. Okay, A lambda expression is a way of specifying a function on the fly, real quick, but it's anonymous because it doesn't have a name. I can't give a name to this lambda expression because it doesn't have one. I can't give a name to it, but it doesn't have a name. It might not be clear why we have these things right now, but I promise you later on it will come into play, okay? So we will have reasons to want these things. So that's a lambda expression. They're anonymous, blah, 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 blah. Here's an important note for you. Sorry, go ahead. Sorry, you're right. Okay, let me revise my claim. I'm going to give a more detailed treatment of this later on, but yes, we'll save the immediately concluding step to later on when I talk about binding. Yes, good question. All right, let's move on. So functions are values. How many of you have heard this statement before? Raise your hands. All right, so all of you should be raising your hands by the end of the course. I've got a present for you. Here you go. No, it was just on the table. You can rip those up again if you want. Functions are values. What does that mean? It means that I can pass around this guy like any other value, okay? I can use it as I wish. That means that, for instance, if I took away this stuff, right? I took away the application, I took away the notation, I can say something like val double, sorry, I'm running out of space here, equals. So I can say, instead of saying fun double, I can say val double equals fn, all that stuff. Okay, it's an expression. Those two things are equivalent. If I say one or the other, it doesn't matter to me. Okay, it's just that the first one kind of looks nicer, so we do kind of like that. But functions are values. That means I can bind it to a variable. It's not special, or well, it is special, but we'll see how that is later. Yeah.
So 2 questions. We can't actually write fun double equals fn.
You can.
We can.
You can, and then I'll talk to you more about that in 4 weeks. But okay. You absolutely can, and that's going to lead us into a very elegant idea called currying. Okay. And we'll talk about it in 4 weeks.
And the second question is, let's say we just like had the double function and we were like using it in code. Are these two things like equivalent? Like we can't tell them apart once they're like defined.
So you're also getting ahead of me again because I'm going to be talking about extensional equivalence later. They're equivalent. If I had that thing and I had that thing, I could not tell the difference between them observationally from using things from in SML. They are completely indistinguishable. They are extensionally equivalent, and I'll talk about that in like 30 minutes. But yeah, good question, good question. You'll hide your Philippine too. Cool. Yeah. Yeah, so equals and greater than sign. When you're doing a lambda expression, it'll have to be this instead of an equals. And in a function declaration, it's just an equals. But it's just a syntax difference. Yeah. All right, good point. Okay. Y'all getting ahead of me. Cool. All right. Lambdas, there's one difference. Oh, hey, there's Polly. I didn't even realize. We have a class mascot, by the way. We have 3. Their names are Polly, all of them. This is Blue Polly. Green Polly's the OG, but she's not here, or they're not here right now. Polymorphism, Polly the polymorphic parrot. This will be hilarious in about 2 weeks. Cool. So suppose I wanted to declare this fact function via a lambda expression. So how would I do fact right now? So, or rather, fact, like the factorial function. Okay. The factorial function, right, is defined such that I realize I'm running into a little bit of sequencing here, but what I wanted to say is I want to say like factorial of 0. So if I want to write Brigham math, fact of 0 equals 1, right? And then fact of, it's a piecewise function, fact of n is equal to n times fact of n minus 1. Like this is how in math I would specify it to you. If I wanted to write a lambda that was fact, well, I'd write, okay, first let's say if n equals 0, then 1. Otherwise, what am I going to put? How do I call myself again with a lambda? You can't, is the answer. Lambdas are anonymous. They don't have names, so they are not recursive. So you cannot, okay? That's the strength of anonymity, okay? If you don't have a name, no one can refer to you. This also applies to, if you don't give your kid a name, they can't get bullied. They'll be like, hey, you there, I don't like your shirt. Who, me? What? I don't know who you're talking about. Same principle applies here, all right? Just close your eyes. That's a little bit of a stretch. Function evaluation. So I already showed you some examples of functions evaluating, right? I showed you like if I use double on 2 or something, then I get 4, right? But function evaluation, the way it actually works, application, if I have an expression that looks like E1 applied to E2, so I have a space here. If I have E1 applied to E2, my rule is first I need to evaluate E1 to a value. Then I evaluate E2 to a value. So let me write this. Eval E1 to val 2. Evaluate E2 to eval. And then 3. Step into E1's value, I'll say. And I'll expand on this in a second here. Okay? There are rules. There are concrete rules we obey when talking about what this programming language, what a programming language does. Okay? So we evaluate E1 to a value first. Every example I've shown you so far, E1's already been a value. Like when I was applying double here, or when I was applying this lambda is already a value. No work needed, but remember that E1 needs to be evaluated first in actuality. Okay? Okay, so like for instance, like if I have this one, I'm not going to write all this down, but we would get a trace that looks like this. So to step through the parts, I have my lambda here, which is already a value, so I'm not really demonstrating that to you right now. But I have this, and similarly to what I showed you at the beginning of lecture, I step the first component of the tuple, I cite the definition of plus, then I step through the definition of multiply to get 12, and then I can step into the value, the body of the function. And there's a little bit more magic that's happening here, which I'll talk about in a second. Any questions so far? Cool. Okay. Yes, and you want to put justification. It'll make your TAs happy, and it'll make you happy because you will get in trouble if you don't. Okay. All right. So stepping into a function, we call the body of a function the thing that's inside here. So this is the body of this lambda expression. That's just like vernacular that we use. But we step into the body once all of the arguments that it's given are now values. So here the body is n plus n, but only once we evaluate these things. Like if I had 2 here, then we step into the body by substituting 2 for n, and then we go here with respect to what the other person that asked me a question was saying. Okay, so I step into the body and I produce bindings. The next natural question is, what are bindings? Now you kind of learned about this in lab, but let's go over it again. Any questions? Cool. Okay. So I kind of rushed through all this stuff. I'm trying to get you used to the syntax. I'm trying to get you used to the machinery that you're using in SML. But the main conceptual thing you got to know about is binding and scope. The reason why it's different to do declarations in SML versus in an imperative language. The reason why we don't have mutability is because of a choice made here. So if I give you a variable declaration, I say val x colon int equals 2, what's it doing? You might say it assigns x to 2. You might say it declares x as 2. I will accept the latter. I will not accept the former. Assignment is different. Binding is not assignment. These are two different things. And the reason why is because of this idea I was saying earlier, where in an imperative program, I change the world to be something. But then someone might come underneath me and then just whip the world from underneath my feet and change it on me. And now x is different. Now x has been assigned. Binding, that can never happen. When I bind a variable, that variable stays at that value forever and ever and ever and ever until the program terminates. Okay? Or it gets shadowed. Well, yeah. So binding is how we associate a variable, a name, to a value. And it is to a value because when we evaluate a variable declaration, the first thing we do is we evaluate the right-hand side to a value. Or at least we try, right? If I said val x colon int equals 4 plus 4, x is not bound to 4 plus 4, x is bound to 8. Fair enough? And if it was looping forever or raising an exception, we would never get the binding. And I won't demonstrate it for you. It's fine. Okay. So binding is not assignment. Why is that? Let's see. So suppose I have this trace of code. X is equal to 2. I declare this magic function foo, and it takes in y and then evaluates to x plus y, where it's referencing this x here. And then I redeclare x at 4. What is the value of foo given 1? Riddle me this. Who's got an answer for me? Yeah. 3. Is it 3? No, it's not. Yes, it is 3. Yes, it is 3, but you're not supposed to say that because you already went to lab, you cheater. So you don't get a high chew. No, none of you can do anything about that. If this had been the first lecture, I could have been, oh my god, it's actually 3. But you know it's 3. Yeah, it's 3, right? Because that, well, oops. That x is completely unrelated to this x. They're named the same. They happen to be named the same. It's a fluke. But this guy, this foo knows what's up, all right? The function foo knows exactly who its main man is here, which is x, all right? That doesn't change, all right? Just as someone else comes strolling in. So again, I already said this, but you change the world in imperative language. But right now, you can't, right? We cannot change that. So x is unrelated here. So let me give you an analogy, all right? This is going to be a hard one, so stick with me here, all right? Suppose that your name is Brandon, all right? Ooh. And you have a 9-to-5 job. Jeez. And your manager walks in and says, Brandon, your performance has not been good lately, I got to say. And he walks out. He walks out of the room. All right, and then you're moping, you're all sad, and then suddenly another engineer named Brandon walks in. You're still in trouble. You are still in trouble. It doesn't matter that someone unrelated walked in. You, me, are still in trouble, okay? The names were the same, but it doesn't change the content. My manager was talking about me, Brandon, not whoever named Brandon that happened to be in the room. So the point is that when I do this thing, when I have this x here, this is x. I bind x to 2. And then this binding of x to 2 exists forever. And then I happen to bind something that happens to be named x. And it's to 4. That's fine. It's unrelated. It's not the same thing. I'm not reaching into a box somewhere, right, labeled x, which has 2 in it. That's not the picture you should have. The picture is that 2 just exists. 2 exists. There's no box. And then x happens to map to 2. X happens to have like a cosmic affinity for 2. And then another guy called x strolls in, and now it's 4. But like every time that I ever referred to this x was the same. It remains the same. Okay, it doesn't go away. I already went through this. Any questions on this? Yeah. Yeah. So if you could no longer reach like this this foo function that we declared, if you could no longer reach that, and like that was the only time that this original x was ever reached, then yeah, you could think of it as it just kind of fizzles out. That's kind of what happens in the background. But generally, you shouldn't really have to think about whether or not it stays, but you can't reach it, or if it just goes away entirely. Because to the user, it's the same, right? If I can't reach it, it might as well not exist. So in our abstraction, we don't really care, right? That's an implementation detail. But yeah, good question. Yeah. Well, let's find out. Oops. I didn't have the setup for lecture. Sorry. Oh. Fun double n int equals n plus x. Unbound variable or constructor. So to reference a variable, it can't be what I'll call free. It can't be a free variable. It has to exist. We have to be in the scope of that variable first. It has to already have a binding in the environment, which is what I'm going to talk about next. Yeah. Yes, you can. That's a construct called let_in_end. I wasn't planning on getting it to it this lecture. I was planning on introducing it in Tuesday's lecture. But yes, you can. And I'll hold off on that because I have a lot of stuff to talk about. But good question. Yeah. If I define x twice in a row. So if I did something like val x colon int equals 2, and then val x colon int equals 4, right? These are unrelated, as I said. But I never referenced this x. So kind of like what he was asking, like if I never ever use this guy, like it might as well not exist. So here, because I never use this x, like it doesn't really matter to you if you can't reach it. If I can never reference this x, anytime I use x, it's going to be the most recent x, because that's the one that was most recently declared. Does that answer your question? Okay. Yeah. Any other questions? Yeah, it's good to have questions. Thank you. Cool. Okay. Oh, sorry. I need to go back to the slides. All right. Let's move on. Okay. So we call the environment in the program the collection of all active bindings. When I produce a binding, or when I do a binding, the environment changes. Every single thing that I know to exist, every variable, along with the value that it's mapped to, is within the environment. So for instance, if I had, So in particular, when I say like val x colon int equals 2, I'll say produces a environment. And the notation will look like this. We put square brackets, and we put the variable slash, or we put the value slash the variable that it was bound to. So in this case, I bound 2 to x, so I have 2/x here. Okay? This is notation. Again, this isn't SML code, but it's my way of denoting what the program currently looks like. So once I evaluate this, I get an environment that looks like that. Okay? But what if I were to immediately do, like I showed you earlier, val x colon int equals 4? Well, now I'm going to displace this binding. It's going to go away. So I'm going to say that 4/x. And something else interesting happens when we get functions in the mix. But let's think about this case first. Okay? If I immediately bind it, I shadow it, is what it's called. I shadow it. This binding is no longer visible. It's no longer in my environment because I kicked it out and I replaced it with 4. We like 4 better. Okay? It's double it. So we are no longer in that variable scope once we shadow it. Okay? And this is our notation. Okay? So for instance, if 5 was bound to x and true was bound to y, you'd see that one instead. Any questions? Yeah. So the thing is that, like, if I were to, like, suppose I did this. Val y colon int equals x, right? If as you're proposing, like, our environment became this, when I like use this x, when I like try to reference that x, like, well, there's 2 x's in my environment. How do I make that choice? And I suppose you could conceive of a programming language where, like, you put both in, you flip a coin, and you pick one randomly. But that's probably not a good idea, right? So what we do is we only ever have one binding for one name at a time, right? Because now we definitely know that this x references the most recent binding of x, which simplifies our conceptual model a bit. Yeah, good question. Yeah. It would. So you're saying this. Val y colon int equals x plus x. And then this will, as you said, produce a binding of 4 to y, right? So we still have the old binding of x, 4-y, right? And you also said that we have like we shadow x here again. And the question is, what should the environment that we produce at this next line be? The question doesn't really change, right? Like, if I were to still say, oh, I want 2 bindings of x, like, the idea is I still should kick out the old binding, because then if I do that, if I have 2/x, 4/x, 4/y, I still don't know which one of these to reference, right? It's not so much like, I would think about it instead like when I reference a variable at any given time, I just look for the most recent binding of it. So at this point, at this program point, when I'm after all of these, the most recent binding is 2x is 4. I don't know about this guy. I can't possibly see that guy because I'm intercepted by this declaration. So the actual picture is, this one. 4/x is the most recent binding. Yeah. I guess it ends up being, yeah, sure. Okay, I didn't realize that, but sure.
Just like to acknowledge it.
To acknowledge that it is shadowed, yeah. I can see it either way. To be honest, this isn't really going to come up, but it's more of making sure that you get it right, that like we're referencing this guy instead of that guy. So as long as if you're aware, like basically you're just adding information, like 2/x with a thing through it is equivalent to this in terms of how I use it. I still can't see this 2/x. That's what I'm concerned about. I want you to know that you cannot see this 2/x from any future bindings here. That make sense?
Yeah, and also, does the
After the line. How do you mean by shift everything? Oh, sorry, yes. So this exists like here, this exists like here, and this exists like here. Yeah, sorry, the alignment is not quite correct. You're right about that. Yep. Yeah. Yeah, so let's get to the function case. I was holding off on the function case, but I think it's time we move on. Good question. So this looks like straight line code. It's basically what I just showed you, but nothing changed about like this. This is no different than like if I did it in an imperative program. The key thing to remember here is that binding is different than assignment only once you introduce functions. Okay? Here, this straight line code, you could write it in like C or Python, and you would get equivalent results. X would be 4 here, Y would be 4 here, so on and so forth, right? But the difference is when we get into a case of having a function bound. So let's say, I don't know what the exact example is going to be, but that's OK. Suppose I bind a function right here. It's going to be funfoo, our friend funfoo, n:'int equals, I don't know, n plus x. OK? Remember I said that we bind things to values. Oh, geez. Bind things to values before we bind, or we evaluate things to values before we bind them to variables, right? So if I'm doing this declaration, I want to evaluate this function to a value and then bind it. It's kind of like val foo equals a lambda expression that goes to this, right? But that's already a value. My point is that when we're trying to think about how to denote the environment here, so this is here, 2/x, what do we write as the thing that we have bound to foo? Right, I want to like denote some value. So I introduce to you lambda expressions, right? In reality, it would be insufficient to say a lambda expression because suppose I put here fn n:'int goes to n plus x. I said this is the value bound to foo, right? But this is actually not quite correct because what if this x, what is this x? What is the x that I have here? It's 2, right? So I can't, it's not quite right for me to write x here. In particular, when we bind something to foo, when we bind a function to a variable, we're binding something called a closure. A closure is 2 things. It is 1, a lambda expression, and then 2, it's an environment. It's a pair of 2 things. When I bind a function, I remember the environment at the time that I bound it, and I store it inside of foo. So when I bind this thing, it's not just this. Okay, let's say I'm going to put in parentheses. It's 1 thing this, and then 2 thing, it's 2/x. All of this is my closure bound to foo. I'm including the environment. It's not just the value. What the extensional effect of that is if I go here, I do val x, sorry if this is messy. If I shadow x at this point, the environment here is going to be 4/x and then the foo thing, right? Is that clear? It's going to be, we still have the finding of the foo, but we also have 4/x. Sorry, this is really hard to see. But that doesn't change what's in here. That doesn't change this yellow thing. Future bindings to x change this top level environment, but it doesn't change what's in the closure. I think I have a better picture for you on a different slide. So another way to remember this is functions are not just values. Functions are elephants. They remember everything. A function, when I bind it, remembers the exact environment that it was in when it was declared. It remembers it forever. So that function can never be changed in the future, right? Because it remembers the fact that it had this 2 for x environment when it was originally declared. Does that make sense to everyone? Yeah. Exactly. This another way of thinking about it is, I'm running out of space on this board here, but basically, like, suppose I were to evaluate like foo of 2. What happens when I do foo of 2 is I want to step into the body of the function, and I want to consult. I want to say it's n plus x, right? That's what I want to say. But what is x? It doesn't consult this environment where x is 4, as in the one with the shadowed variable. It consults this one, its own private environment, the state of the world at the time where it was declared. I can't change that on the function. The function will always evaluate knowing what x was. This is equivalent to saying that it just like stores all bindings inside of itself. Yeah. Everything but the unrelated bindings, if it doesn't use them, you don't really have to think about. It's not really important. Again, it's just kind of this distinction of if we don't use it versus if it's not there, it doesn't really matter to me. But yeah, I saw another hand. Yeah. Yes. So let me try to write this out with more space. So you're correct that when I declare the function foo, I have to have x defined, right? I can't use the x if it's not there. But later on, like there are kind of two different concepts of x. So I do like fun foo n colon int equals x plus n, right? And I already had here like a binding of 2 to x. I'm not going to rewrite it. So here, my environment after this step is going to be 2 for x, and then it's going to be fn n colon int goes to x plus n, along with the environment 2 slash x. This whole thing is what I bind to foo. Right? So it's two things. I have 2 bound to x, and I have this big yellow monstrosity bound to foo. Right? So then later on, when I do val x colon int equals 4, I get 4 slash x. Again, I get yellow monstrosity bound to foo. But the point is that these two things are the same thing. So there's a 2 for x in here that is still there. It's not at the top level. I can't see it from future bindings. If I referenced x, I would still get this guy. But function foo knows about the original x that was bound up here. Does that make sense for everyone? Yeah. Two plus x, it's pretty much equivalent. If you eagerly substitute in everything, so you're saying, why don't we just forget about this idea and like just write this, right? Equivalent. Different ways of thinking about the same thing. If you do that, that is exactly what's going to evaluate to the same thing. Yeah. If I remember my bindings explicitly and I look them up in like a little table I have to myself, or if it's like already there, like we're going to see the same behavior. Good question. I feel like I'm owed 2 high juice right now. Oh, I'm sorry. I'm not the best at throwing things. All right. So functions are elephants. They remember everything. I know this is confusing. I got to move on. Okay. But I hope everyone's got the idea of why this is important. Because I can never change the behavior of foo. The implication here. Oh, I also had a little picture for you, but it doesn't really do much more than what I put. When I bind a foo here, oh, actually, it's exactly the same. I used 2 and 4 and everything. Great. When I bind this closure, if I do anything after this foo function, it never changes. Foo's behavior cannot change based on bindings that happen after foo. That means that I can never change the world on myself. That means that code is modular. If I'm looking at a piece of code, everything that happens after it in a functional program is not important to me because my function will always behave the same. It lives in a nice little world where it remembers everything that happened up to its point, and what happens after, whatever, right? So the point is that because of immutability, because of the fact that I can't change this environment, the effect is that functions cannot change their behavior based on future bindings. Okay? That's the goal here. That's what I want you to get out of this. Okay? The technical details we'll work out later. Okay? Cool. Quiz time. All right. Get into your houses. Everyone get up and get into your houses. This is where we're taking a quiz together for 5 minutes. Blue team here. Yellow there. And then red go, or I love Brandon. Go to the back. Blue team, like as a house blue team, your color is red, okay? Jesus, you bunch of jokesters. Let's go, let's go, let's go, let's go. Come on. So, I love Brandon in the back. Red team here, yellow here. Yellow on my right. I love Brandon in the back. Red team on my left. Blue team, Jesus. Yellow on my right. Yellow here. Okay, is everyone about done? I'm going to call it here. All right, submit if you haven't already. Also, there's a timer on the quiz. I forgot. So you should be unable to submit pretty soon. Okay, TAs, can you please grade that for the rest of the lecture? Thanks. All right, they'll do whatever I say. It's fine. Okay, back to lecture. Settle in, settle in. Laptops away or take notes, whatever. Cool. Okay, hopefully that was fine. We're going to be doing this for every lecture from now on. I realized it was a little buggy. I'm sorry about that. I may or may not have made it at 2 a.m. last night. But anyways, quiz time. That's over. Let's move on. I'm not going to finish the rest of the lecture in the next 30 minutes, unfortunately. But it's fine because I took some material from lecture 3 and I moved it up to this lecture. So I'll see you Tuesday and I'll tell you the rest of the stuff I plan to talk about. Let's see what we can make it through. Okay? But yeah, so pattern matching. So we already saw how we can write variable declarations using that syntax, right? We say that val x is equal to, in this case, 1, 2. But if I bind a tuple to a variable like that, then how do I get out the values in it? I said that x is equal to 1, 2, but now that I have x, which is of type int star int, how do I get out the components? I can't. It's x. It's a tuple, right? I can't do, for instance, let me show you actually. I can't do, if I do this, if I do x plus 2, I'm going to get a type error. Why? Why do I get a type error? What's the problem here? Yeah. Types don't, well, specifically. Like.
I mean, it's int star int with.
Yeah, that's good enough. All right. That was fine. That was fine. All right. Yes, there's a type error. I shouldn't have done that. So to get the values back out, I'm going to use something called a pattern. In the same way that we use tuples to put things into tuples, we use tuple patterns to take things back out of tuples. Okay? So we say val x comma y colon int star int is equal to 1, 2. And if I show you this on the SMLNJ REPL, we get two bindings, right? X pattern matches to 1, y pattern matches to 2. Okay, so I get them back out, and now I can use them. Now I can say something like x plus 2, Okay, but this is just one application of patterns, and this produces that environment, as we said earlier, right? 1 is bound to x, 2 is bound to y. Okay, you have a question? So if I ran this, I would have x, the tuple bound to x. If I ran this, I would now shadow that tuple with this. So this would still be the output environment. Yeah, good question. Okay. Yeah. So what I mean by that, I guess, is like if I have this x equal to 1, 2, right? Like if I say that, val x equals 1, 2. I have this x, and it's just 1, 2. What I mean by unpacking is I want to use the 1 and the 2 inside of the tuple, but I can't, right? How do I access the 1? Suppose I put in some secret into the tuple. I want to get it out. How do I do that? So when I say unpacking, I mean that I'm just using bad names. Here now, x remains this tuple, and now y is the first component, and z is the second component. So that's what I mean by that. Does that answer your question? Yes, but that's not super important. I'll let you play around with that on your own, but yes, you can do that. Yeah, good question, though. Cool. Okay, but yeah, we can get this environment out, and I kind of got to go for the rest of the lecture. So what is a pattern? A pattern is a way of describing the form of a value. Like values can take forms like 2, or 3, or 1, 2, or true, or anything in between, right? Those are all things that can be values. But suppose that we want to break down that value. We want to be able to match to it. So patterns should be able to describe them. So we use x, y to deconstruct the value 1, 2. Why? Because if I put them up next to each other, I have x, y is my pattern. I have 1, 2 as my value. These things match, right? I see that these two things are in the same place. So I match this to that, and I produce a binding. And then I match y to 2, I produce a binding. So that's what I mean when I say pattern match. We take a value and we query it against a pattern, and optionally we might get bindings out. Okay, and I'll show you the mechanism by which we do this in a second. So, but the right-hand side of this val binding doesn't need to be a value. If I said val x equals 2 plus 2 colon int, right? This could be an arbitrary expression. So it doesn't matter what I put here, so long as the types match. For instance, suppose I had val x comma y colon int star int. Suppose I had this equals 2. Does anyone see a problem here? Yeah.
The right-hand side is just an int.
It doesn't type check, right? Not only did I put this type annotation here that says it should have been something else, but even if we know this pattern expects a tuple. That's not a tuple, right? So yeah, we would get a type error here. That's a mistake. So oh yeah, I have these things up here to kind of remind you of the theses every now and then. But a types guide structure. When I have my type here, this int star int and this pattern, that's correlated with the pattern itself. So if I have a tuple pattern, I expect a tuple value here. So what I might say also is that if I have the pattern x comma y, I expect something of type t1 star t2 for some types t1 and t2. Right? It could be int star bool, could be bool star bool, could be string star int. Doesn't matter to me, but the pattern expects that we should have something that is of that type there. And I should have type annotated this anyways, but yeah. So it needs to be a tuple that has 2 things in it. Otherwise, if I was able to do it, I might try to unpack 2. I might try to extract this and this out of 2, and that doesn't make sense, right? That's an error. So the type system prevents us from doing that, because otherwise we'd have to say runtime error. I wasn't able to do it, which is a mistake. We should try to avoid doing that. Yeah. Yeah, I'm making a mistake here by not type annotating. For this portion of the course, assume that you must type annotate everything. We're going to see later on that we can omit them, but please, please, please use type annotations right now. It is better for writing more clear code, and it will help you think about the types. But later on, we will see that we can omit them. Yeah, good question. OK, cool. So we can use patterns for things other than tuples. That's why I erased this big board. I forgot about that. Right, so if I have patterns, I have a bunch of different kinds of patterns. Actually, you know what? I'm not going to write it. It's up here. So I have variables like x, y, z. We saw this when we said val x equals 2, or colon int equals 2. Right? We bind it to the variable x. We also have the wildcard pattern. Let me show this to you in the REPL. So if I did something like val x colon int equals 2, I get a binding to x of 2. But what if I did val underscore colon int equals 4? Nothing got printed out. Can anyone hazard a guess as to why? Nothing got printed, but I didn't get an error. I didn't get something malformed. I still am in the REPL. Why?
I don't know, but what if we just enter underscore?
Unfortunately, that's what Python does. This would work in Python. But no. So what's happening here is that the wildcard pattern doesn't produce a binding. It just matches to anything. It matches, but it doesn't produce a binding. Matching and binding are 2 different things. So if I said val x colon int equals 2, I produce this binding, but if I say val underscore, here now, I don't expect a binding back because I didn't give it a name. Wildcard matches anything, but it's nameless, essentially. Okay? Yeah. We'll see with more. OK, actually, let me show you a specific example. Suppose I want to get the first component out of a tuple, but not the second. I might write something like x, I keep reusing x. I hope you realize this is different each time. I don't really care about the name. And I produce just the binding to 1. I didn't want the binding to 2. Otherwise, I might have to come up with some name. And that would clutter my code. It would clutter my thinking. It would be unimportant. So judicious use of wildcard is important for writing clean functional code, clean SML code. Yeah.
So is that all wildcard is used for, which is just to clear other things?
For getting rid of parts of patterns that you don't care about, yeah, essentially. Yeah. We'll see more examples later, but yeah, good question. We also have constants, so we can do something like, oops. You'll get a warning here, but this succeeded. Basically, a pattern, which is this guy, can be a constant like 2. This means I'm expecting 2, and I'm trying to bind it, and I'm not going to produce, or rather, I'm trying to match it, but I won't produce a binding. But if I did this, well, 2 doesn't match to 3, so this should be an issue, right? And in fact, we're going to get an exception. Okay, I can't really stop you from doing this because anything could be on the right-hand side here. But what's happening here is that we're trying to match to 3 with 2. That doesn't work, so we get an exception. Okay, that's what constant patterns do. It's generally not a good idea to use them in a val binding like this. We'll see other cases where we can use them. And then tuples, I already showed you this. Okay, I kind of need to go move along. So you could have inferred this, but the form of a val binding is I say val, I give you a pattern, I give you a type, and then I give you an expression, right? That's why here I was able to write. That's why I was able to write things like, val 2, or I could say val x comma y, or I could say val x, or I could say val underscore, right? Because here is just any pattern, right? Any pattern goes there, and then that's equal to some expression. And I already showed you that if you try to do this, it's not going to type check, right? Because the right-hand side here is a tuple, and the left-hand side is a constant of int type, right? It's an integer. It's expecting an integer, which a tuple is not. So this will not type check, so it will never run, right? Because ill-typed programs do not run. But if I did it slightly differently, like I just showed you, if I did val 2 equals 1, this runs but produces an exception, okay? There's a distinction here, right? One of them never runs, one of them does run but gives an error. Cool? Does this make sense to everyone? Okay. I'll give you like a second to write, I guess. Okay, but I gotta move on now. So I already showed you double, but suppose I wanted to do something more complicated. I already used this, but let's talk about it. We have these if expressions. The syntax is this. I have fun is even, and then if n mod 2, where mod is the modulo operator, is equal to 0, then I return true. Else I return false. An if expression is an expression. I can bind it to a variable. I can bind it in a function declaration. It is an expression that can be added, it can be subtracted, it can be used like anything else. Except that I've shown you something really, really concerning. Do not do this. Do not do what I've shown you here. Does anyone have an idea as to why that is, actually? I don't know if you went over this in lab. Don't do this. Yeah.
Is it because maybe n mod 2 equals 0, like parentheses, like order of evaluation?
Yeah. Well, it does evaluate first. That's true. Yeah. Yeah. It's already a bool. I'm putting a bool into a test on that boolean, and if it's true, I'm returning true. If it's false, I'm returning false. Why am I doing this? So here's a brief interjection. I gotta get up about this. So we have the if expression. It looks like this: if xp1, then xp2, else xp3. It has certain rules. I'm gonna be a little fast about this. Sorry, I'm a little behind. But these two branches here need to be of the same type. Why? Because I might get type unsafety, right? If I can condition on something and produce things of two different types, I cannot tell you what type I get out. Because, for instance, if I have if Sasquatch is real, then 2, else string foo. Depending on if Sasquatch is real, I might get 2, the integer. I also might get foo, the string. That's bad, right? So we're going to constrain that these two things need to be of the same type. But back to the warning, anyways. The reason why this works, what this if expression really does is it evaluates E1 to a Boolean. Then if it's true, it goes to E2. Otherwise, if E1 is false, it evaluates to false. Then we go to E3. That's what it does. So let's try is even 2. Okay, let's trace it. And this is a lot, but by the definition of is even 2, I'm going to get if n mod 2, so 2 is bound for n, 2 mod 2 equals 0, then true else false. I use the definition of is even to get there. Then if 0 equals 0, because 2 mod 2 evaluates to 0, so I use the def of mod. And then 0 equals 0 is true, so I step to this. I get true. So I get if true, then true else false. That's a little redundant, isn't it? It's really redundant. Sorry, past me thinks it's really redundant, so I have to say that now. It's really redundant. Don't do this. Similarly, if I put in is even of 3, we'd get this whole thing, but it'd be if false, which is similarly redundant. So never write if e then true else false. Actually, the grader will complain at you if you do, but I feel like giving this information now. So don't do that. It's a style error. it's also just not good code. Like, you should be aware that these things are equivalent because bools are bools, and if is just an expression. Okay, so you can write like if something, then E2 and E3, where E2 and E3 are not true and false, but don't do this. Okay, that's just something I wanted to say. Okay, we can write the factorial function I told you about earlier using a fun declaration. So it's fact that takes in an input. If the input is 0, then it returns 1. Otherwise, if it'll return n times fact of n minus 1. This is clearly the factorial function, right? This makes sense? And it looks a lot like the mathematical fact I wrote for you earlier today, which is a nice thing about SML functions is that they just look like equations. They look like equations, okay? And that's the strength. But I'm going to show you a different way to write this, which is that we can use these function clauses. So using function clauses, we're going to be using the patterns I just taught you about. With patterns, we can say, if I get an input, first I'm going to step linearly through the clauses. Suppose I have fact of 3, okay? I take the 3, and I go to the first clause. Does 3 match to 0? I see shakes of the head, right? It doesn't, so I go to the next clause. Does 3 match to any variable n, like a binding to variable n? Yes, it does, because this pattern matches to anything. So if I had fact of 3, I would go into this body with the binding of 3 to n. So fact of 3, I'll write down, evaluates to 3 times fact 3 minus 1, right? Because it didn't match to the first case. And if you iterate this process enough, I'm not going to do the trace for you now, but you can imagine like this is going to be 2, we're going to keep going, and eventually it'll match to 0, right? So that's the reason why. So if we write this way, we don't need to use the if expression. Pattern matching is more powerful than if expressions. If I use pattern matching, I can match on precisely the value without needing to get this equality thing involved. It might not be obvious to you why this is different with just a simple example, but with like things like tuples, with things like other types of things that we'll see later this semester, you're going to find that pattern matching is really, really powerful for saying exactly what you mean to do. It makes for clean control flow. So we prefer to write this function this way over this way. Okay? The second way over the first. Okay. And we call those function clauses. That's the general syntax. I'm going to skip over this because it's not super important, but that's what happens. And then I'll say one last thing, which is that these outputs in each clause have to be of the same type, for the same reason as the if thing I told you earlier. If they were different types, we could possibly return different types in different branches, which is a big no-no, right? So they need to be of the same type. Okay? Function clauses need to return the same thing. All of these outputs are of type int. Okay, I'm going to speed along here. I'm going to talk about evaluation for just a little bit because I don't have a lot of time. Okay. But before, does anyone have any questions that they really need answered before we talk about equivalence? Yeah, I made this lecture by like consolidating some content from lecture 3 and pulling it in, and I already knew at the beginning of this lecture I wasn't going to get through all of it, but that's fine. Okay. So with binding and scope, we talked about how variable binding is different than assignment, right? When functions get involved, I can never change my mind. Behavior of my functions is always the same. That's the difference, right? Which means that I can never have a function like increment where if I call increment, it returns 0, 1, and then 2, and then 3. Because of binding, I always get pure functions. Remember the term pure I told you last lecture? It means a mathematical function. Same outputs given same inputs. And this is really nice because it lets us reason equationally. So I already stressed to you that like binding gives you modular code, right? I only have to think about what happened before a function to reason about what the function does. I already told you this, but binding preserves function equivalence, basically. As a direct result of binding, right, if I have f of 2, I can always say that f of 2 will return me the same thing, because it cannot change its behavior based on a binding that happens after the function f was declared. So f of 2 is f of 2, is f of 2, is f of 2, always. Okay? So I promised you that we'd think about math. I promised you some math. I'm sorry if you don't like that. But this is a class about functional programming, and there's a lot of math involved here. So we're going to have a new definition here, and this is an important one. This is an important thing I tell you now. This is a definition of extensional equivalence. And two expressions are extensionally equivalent if they either evaluate to the same value, they both loop forever, or they both raise the same kind of exception. You might have gotten this in lab. So we write this shorthand E1, and we do E1 equals with this little tilde over it, E2, when they're extensionally equivalent. So to put in mathematical notation, what I was saying earlier, if I have f of 2, this is always true. F of 2 will always be extensionally equivalent to f of 2 because I cannot mutate the world. I cannot change the function's behavior. So in any context, it doesn't. So instead of needing to think about, oh, what's increment of, what is this? You have to say, oh, well, if you called it 2 times, then increment is 3. Or if I called it 3, no, there's no if. F of 2 is always just f, or rather, let me concretize. Fact of 2 is always 2. The factorial function I showed you will always return the same input. And that means that in any context, in any time that I'm thinking about what factorial does, I know precisely what it does. It always returns this, okay, for the factorial function. Yes?
Does this mean that, like, all, like, infinite loops are extensionally equivalent?
Of expressions at the same type. Extensional equivalence is only on expressions when they have the same type. But if I have 2 loops that are of type int, yes, they are extensionally equivalent. Doesn't matter how they loop. If they loop forever, they are. We don't necessarily need to be able to prove that, but if they loop, they are. Yeah. No, we only are talking about extensional equivalence on like well-formed SML programs. An ill-typed program is not well-formed. It's not well-typed. Generally, we disconsider all ill-typed expressions or programs. Yeah, good question. So yeah, for instance, 2 plus 2 is extensionally equivalent to 4, but is also extensionally equivalent to 1 plus 3, right? Because they all end up at 4. So we already talked. Oh, sorry. Go ahead.
Yeah, just want to know.
Yes. In the 2 sides from that. The fact that plus works on both reals and ints is like frankly a mistake in the language. Don't think about it. It's not worth your time. It's literally one of the only special cases of that in the entire language. Don't think about it. The real version of plus is not equivalent to the int version of plus. But in general, when we talk about plus, we'll be dealing with just the integer addition. Okay. It's really a shame I have to like disclaim that. it's so not nice. Anyways, yeah, like good question. So we saw something which looks already like this, right? We said that like 1 plus 3 is extensionally equivalent to 2. 4. We saw something like this already, right? We saw reduction. So 1 plus 1 reduces to 2. We learned, right? It simplifies to 2. But 1 plus 1 is also extensionally equivalent to 2. But what's the give? Why do I have 2 of these things? Don't they look the same? They're not the same. So I'll say this to you, and I have a slide talking about this, but I don't really feel like going fully into it. Reduction is stronger than equivalence. What I mean when I say that is that if I have that E1 reduces to E2, then it's always the case that E1 is extensionally equivalent to E2. This means that this has, like, in a sense, more information than this. Saying this does not imply this, right? Because I'm really out of space here. Jeez. Saying extensional equivalence does not imply reduction because I also know things like 1 plus 3 is extensionally equivalent to 2 plus 2. But it is not the case that 1 plus 3 reduces to 2 plus 2. Right? That would be an absurd statement to make. We do not simplify 1 plus 3 to 2 plus 2. But the extensional behavior, what both of these expressions eventually do, is the same. So we use extensional equivalence, but not reduction in this case. Reduction is too strong. But if I knew that these two things reduce to each other, if E1 reduces to E2, then I would also necessarily have that E1 and E2 are equivalent. Okay? That's the meaning of the next slide that I'm just going to show you. But doesn't really matter. I rendered you a nice graph here, but basically the idea is that there are arrows going from this to that, this to that, this to that, this to that, so on and so forth. The arrows show reduction. If I have 1 plus parentheses 1 plus 2, that reduces to 1 plus 3, and 1 plus 3 reduces to 4. Similarly, 2 plus 2 reduces to 4, so on and so forth, right? All of these are just simple arithmetic. But the idea is that reduction is one way. Reduction is like a road, and all roads go to Rome, or in this case 4, right? We're going to end up in the same place no matter what. So if I pick any two expressions, any two nodes on this graph, they are extensionally equivalent. They all end up at 4. But it is only the case that 1 plus parentheses 1 plus 2 evaluates or reduces to 1 plus 3. This does not reduce to that. This does not reduce to that. Does that make sense to everyone? I'm not going to write down like explicitly what I'm saying, but the idea is that like we're going to the same place, and sometimes we end up at exception here, or sometimes the graph is infinitely long, and that means we're in an infinite loop. Okay, you can imagine that in your brain. But for values, for expressions that are valuable, right, that evaluate to values eventually, it looks like this. Reduction is one way. Yes. Reduction is different than. Yes, yes. They're a notation that looks similar. But for this one, for reduction, you'd type dash steps 2, right? But implication, you'd use like dash implies, and they're like, I think they're pretty similar looking, but I think they're actually slightly different. But like in terms of the notation I'm using, they're actually different. Yeah. Good question. Cool. I have very little time left, but this is the important thing to talk about here. So referential transparency means if I have E1 equivalent to E2, anywhere that E1 appears in a program, I can replace it with E2. I have a mathematical proof that in SML, you will always have the entire program behave the same. You can swap equals for equals. How many times in a math class have you done that? You knew that like there was some equivalence, like say that like 1 plus 2 plus da 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 plus n. There's a famous equivalence for this one, right? It's what? N times n plus 1 over 2? Maybe minus 1, I don't know. We know these two things are equivalent, so we can swap them for each other no matter where we see them. Is it wrong? No, it's correct. Okay, cool. All right. I didn't prepare this. They're equivalent, so I can swap them for each other whenever I see them. Same thing with my code. I should be able to think about my code like I think about a mathematical expression that I'm trying to prove something about, because I want to prove stuff about my code. So I can replace 2 plus 2. If I see it in an SML program, I can just go and I can replace it textually with 1 plus 3 or anything equivalent to 1 plus 3 anywhere I want. The behavior will not change. I will always get the same thing out. That's not always true in an imperative program, right? Because if I have f of a function called f, I can't just stick it wherever I want because it might do something. It might mutate something. It might loop forever. We're thinking about right now like for things that don't. Yeah. It might like mutate some state. So I don't want to be able to put that. I can't put that wherever I want. So we can swap equals for equals, and this is a concept I'll call equational reasoning. Reasoning about your code like you'd reason about a string of equations. A equals B equals C, so on and so forth. This is the last thing I'll say to you this lecture, which is I want you to think about referential transparency by a different name. I call it the refactoring lemma. A lemma like being some like a helper theorem, like something you can use in a proof. Referential transparency tells you can refactor your code for free. Suppose that you're an engineering manager at a tech company named after a fruit that grows on apple trees. Okay, and you hire an intern. You hire an intern for the summer, and they say, "Oh, boss, I got this PR for you. It's great." And you look at it, and it's in standard ML because Apple uses standard ML, of course. They don't. And then you see this. I'll let you gaze at that for a second. What the hell is this? What am I looking at? I'm looking at a mess. I'm looking at not quite spaghetti code, but something close to it. I'm looking at a mess, really. Right? Like, can you easily think about what this does? No, I have to step through every single case, right? It's pretty gross. Let's solve it using referential transparency, shall we? So, the intern didn't take 150, or they took it a long time ago, and they forgot about equivalences. So what you need to do is, so here, for instance, if flag is set, then we use flag is set. But under the then branch, we know flag is set is true, right? And here, if permission granted. But here we know that we're in the else branch, so permissions granted is false. So let's step it. So if I replace flag is set for true, I replace permissions granted for false because they're extensionally equivalent. I can swap them I can substitute because they're algebraically equivalent. I get this one. But now I see another thing, right? Isn't it also stupid because I'm doing true and also, where and also is the logical and operator? Isn't it true that true and A is always A, right? There's no point to doing true and something. So I can refactor that. So I'm going to get this, okay? But, oh, what's this? It's something I showed you earlier this lecture. I have if something, then true, else false. And we know that if permissions granted, then true, else false, is the same thing as permissions granted, isn't it? So let me refactor that once more. I get if flag is set, then permissions granted, else false. But wait, it looks like the only time we ever get true is when both of these conditions are true. Isn't that the same as anding both of them together? So if I do this, I get that, which is extensionally equivalent, and therefore it's a free simplification. I can always replace the intern's mess with flag is set and, well not and also permissions granted. The refactoring lemma gives us that for free. Referential transparency gives us that for free. We can always simplify our code via doing very simple equivalences, because it was a big leap to go from the intern's code to that, right? But each step I showed you was pretty simple, right? I just pointed out like a small thing that could be simpler, and we carried that along with us. We did a small extensional equivalence step, and eventually we ended up somewhere a little bit far away. But here's the fun thing about extensional equivalence. It's what we call an equivalence relation, which means it's transitive, meaning that if I have E1 equivalent E2 equivalent E3, then I also have E1 and E3 are equivalent. I can do it as many times as I like. I'm giving you the math, but you can probably think about this conceptually, intuitively, pretty easily as well. So the point is, I get simpler code. And the point is, referential transparency saves lives. It saves my life as a manager anyways. So I have more stuff, but I'm not going to be able to tell it to you. So class dismissed. I'll see you Tuesday, and we'll pick up where I left off.